At the CFA, and I'll be starting the Carl Sagan Fellowship in September. I'm interested in extrasolar moons, moons around exoplanets. My bias view, because this is what I'm interested in, would be that exomoons will be playing an increasing role in our study of planetary systems in the future. And if habitable moons are common, then the nearest target for one of these Alpha Centauri-like ships is to...
David Kipping has been hunting exomoons for 16 years, moons around planets outside our solar system, objects that should exist. That logic demands must be there, but after thousands of exoplanets discovered, the count confirmed exomoons remains 0. In 2025, he finally got his shot, 60 hours on the James Webb Space Telescope, the most powerful instrument humanity has ever built. Pointed at Kepler 167e's, the closest thing to Jupiter we've ever found orbiting another star. If any planet had moons, it would be this one. The data came back, and buried in the noise was a signal. A massive signal. Over 12 sigma significance, the kind astronomers dream about. An Earth-sized moon transiting in front of the planet, it looked perfect. Too perfect. And after months of analysis, trend modeling, Gaussian processes, and every statistical trick in the book, Kipping realized something devastating. The signal wasn't a moon, it was probably a star spot, a tiny dark patch on the star's surface that the planet passed over during transit. 16 years, the perfect planet, the perfect telescope, and the universe gave him a false alarm. Hit subscribe. Because what happened next isn't just about exomoons. It's about what happens when you chase something for your entire career and the answer keeps slipping through your fingers. When NASA launched the Kepler mission in 2009, Kipping was convinced it would find exomoons, a meter-sized telescope designed to find Earth-sized planets transiting in front of their stars. By the same logic, Earth-sized moons should be detectable too, so he created a project to find them. After 6 studies and 8 years of trying, the universe didn't cooperate. Earth-sized moons just aren't that common. The biggest moon in our solar system is 2.5 times smaller than Earth. Kipping hoped the universe would be more diverse than our backyard, but Kepler wasn't sensitive enough, so they moved to Hubble. In 2018, his team secured precious Hubble time to observe one of their favorite Jupiter-sized exoplanets, and remarkably they found a beautiful, crisp exomoon-like signal, a dip in the light curve that implied a shockingly large moon, somewhere between Earth and Neptune in size. But no one had ever predicted moons could form that big. Some thought it was too crazy. And Hubble is known to have subtle, challenging systematic noise sources that can create fake signals. When they requested another transit to confirm or deny it, the proposal was rejected, over and over. The community was so skeptical that it became politically impossible to resolve the mystery either way. The object, Kepler 1625b, was benched. Hope renewed when JWST successfully launched on Christmas Day 2021, a whopping 6.5 meter telescope in space. It collects so much light that calculations predicted it could detect transits of moons as small as Ganymede, Callisto, and Titan. For the first time in human history, we had a telescope powerful enough to detect moons as small as those we know exist in our solar system. If Kipping reported the detection of a Ganymede-sized exomoon, no one could say a moon that big is impossible. At least one of the 2 issues with previous claims seemed dissolved. But what about systematic noise? When they were proposing to JWST, this wasn't well known. Early release science programs showed no indications of major systematic noise effects. All the news was about how great JWST was doing, performing better than expected. So they simulated JWST data for a bunch of exoplanets to see which ones were best suited for detecting exomoons. One gorgeous planet stood out, Kepler 167e. It's within 10% the radius of Jupiter and within 1% of its mass. Yet it orbits its star every 3 years, around a slightly cooler star than the Sun, meaning the planet should be a very cool 130 Kelvin. Pretty similar to Jupiter. This transiting planet was and remains the closest thing to Jupiter we've ever seen. And given the dozens of moons around Jupiter, surely 167e would have moons too. In the original proposal, they predicted that if 167e had an exact clone of the Jupiter moon system, they should strongly detect the presence of a Ganymede in 84% of random configurations and a Callisto in about half. The big downside? Getting JWST time is incredibly competitive, oversubscribed by about 10 to 1. Their first try was rejected, but in cycle 3, everything lined up. They were awarded a whopping 60 hours of data, unprecedented for a transit observation. Many exoplanet proposals are far less, maybe 5 hours. For them, such a huge request was unavoidable because long-period planets like 167e take their sweet time to transit, but being given so much data came with a huge weight of responsibility not to screw it up. The observations were taken starting October 27, 2024. They knew they had 1 year to publish before the data went fully public. On the day the data came down, Kipping asked his team to record them watching it happen. Such was his extreme optimism. His PhD student Ben Cassese had led the proposal. Together they stared at the screen hoping. The transit of 166 appeared as a gigantic, clear dip in light. Immediately there was relief that they'd at least timed the observation right, but as they stared at it, there was a growing sense of foreboding. Strong systematics were visibly present in the data, spurious noise sources that would occupy Kipping's days and nights in frustration over the coming 12 months. They'd used the near-spec instrument in prism mode, collecting the entire spectrum of light rather than using a filter, but because they collected so much light, they had to use a very short integration time. Each data point spanned just 1.6 seconds. They had over 134,000 of them, but there are limits to how many points can be measured before the detector needs to reset. They hit that limit 5 times. After each reset, the brightness of the star seemed to suddenly increase. That's not real. That's just an artifact of the detector. Even worse, within each 10-hour segment, there was clearly a slow trend downward. Again, that's JWST causing that, not the star. A classic technique to deal with systematics is to look at other stars in the image and use them to calibrate your data. They'd done that successfully with Hubble, but unlike Hubble, the field of view was so tiny that there were no other stars in the images to compare to. They were up the river without a paddle. For the first 4 months, Kipping had to invent an entirely new statistical technique to deal with the problem. After that side quest was completed, they were finally able to run their fits on the data. What they found was genuinely shocking. It started screaming exomoon at them, a big exomoon, about the size of Earth. When Kipping first saw this, he was both excited and terrified. Excited because they had a signal, a bloody huge signal, over 12 sigma significance, the kind of statistical significance astronomers fantasize about, but also terrified because it seemed too good to be true. After all, this wasn't his first rodeo. The next step was to see what the FITs were doing. Where were they actually placing this exomoon? Plotting it up, the FITs had placed the moon right on top of the planet, which was so huge it shot right off the graph. But what's really worrying is that location implies a moon very close to the planet, closer than Io is around Jupiter, an almost atmosphere skimming moon. After many years of moon hunting, Kipping has learned to be deeply skeptical of these kinds of signals. Their models normally assume a star is homogeneous, a plain, boring star. But any weirdness like a flare or star spot means the model of the planetary transit isn't quite right. The moon model sees that deviation and thinks it can explain it. Naively, it looks like you've detected an exomoon, but it could just be something slightly off with the star or planet model. They tried a bunch of models: linear, quadratic, exponentials, and more. Every time they saw a big moon, but its properties varied substantially. Finally, they turned to Gaussian processes, a sophisticated technique that doesn't assume a specific form. It models a memory-like process in the data. On top of this, they tried different ways of processing the raw JWST data itself. One widely used package called exotic, a custom algorithm that was much more conservative, and an entirely new reduction package Ben wrote from scratch called Katadine. In the end, they presented a grid of 3 different reduction codes and 4 different models, 12 different possibilities altogether. Across these 12, 7 found strong evidence for a moon, but amongst the 6 Gaussian process models, only 2 bore out. The more sophisticated models seemed to largely kill the moon, a possible warning sign. One elegant way of seeing what's going on is to look at the data and ask, where does each fit find the strongest evidence for an exomoon? Which part of the data is really driving the story? They all seem to consistently suggest the signal was driven by two locations, one right in the middle of the transit and one just after, but the Gaussian processes didn't see the second signal. The only signal all methods and reductions could agree upon was the one in the middle of 167 Mies transit. Now, planet models typically assume a boring, homogeneous stellar surface, but if there was a dark spot on the surface as the planet passes over it, it would introduce an upwards bump in the light curve. They've seen these star spot bumps in countless transit light curves before. If the planet and moon pair enter close together, the flux decreases by their combined sum. And then, if the moon eclipses the planet while both are eclipsing the star, the flux will temporarily increase, since now only the planet is blocking starlight. This is known as a syzygy event, and it's highly degenerate with star spot crossings. 4 years of Kepler data showed no clear evidence of spots on this star, but the JWST data are so much more precise that small spots could have evaded Kepler's detection yet still appear here. They found that such a scenario could plausibly explain this event. Even worse, the spot is likely only a little cooler than the stellar photosphere, meaning across JWST's spectral band, they wouldn't expect obvious chromatic changes. In other words, it would look very moon-like. This doesn't prove the Wiggle is a star spot. It could still be a very close-in Earth-sized moon, but they have a really good alternative explanation. For Kipping's team, it didn't meet their standards of evidence. There's just too much ambiguity, and so they leave JWST empty-handed, at least for now.